Title of the module: Spanning Trees in Graphs. Today we are going to learn about spanning tree in graphs. Recall that a subgraph H of a graph G is a spanning subgraph of G if H contains every vertex of G. Also, in the previous module we have seen that a tree is a connected acyclic graph. Now let us see the definition of a spanning tree and spanning forest. The definition: a spanning subgraph H of a connected graph G such that H is a tree is called a spanning tree of G. A graph is called a spanning forest if each of its components is a spanning tree. Let us see the definition of a cotree. The cotree T star of a spanning tree T in a connected graph G is a spanning subgraph of G containing exactly those edges of G which are not in T. To better understand the concept of the spanning tree and the cotree, let us now see some examples. I have a graph here. It has got 5 vertices and 7 edges, and as you can see that we have created 2 spanning trees here. First, let us see the spanning tree T1. So, to recall the definition of the spanning tree, a spanning subgraph of a graph that is a tree is said to be a spanning tree, and you can clearly see that it is a spanning tree because there are no cycles and all the vertices, all the 5 vertices have been covered, and it is an acyclic graph. So, it is clearly a tree. And likewise, moving on to T2, you have these edges here E1, E5, E7, E4, and you can clearly see that this is also a spanning tree and a different spanning tree here, and this is also a spanning tree of the graph G, and both of them can be called as spanning trees. You can even try to find many more other spanning trees for the same graph. Now let us explore the concept of the cotree. A cotree of T1 is here marked as T1 star. As you can see that this is the tree, and all those edges that have not been covered in this graph have been covered in this graph. So, you can see that the edge E6 does not exist in T1, but it exists in T1 star. Similarly, the edge E6 also does not exist in T1, but it exists in T1 star, and likewise the edge connecting these 2 vertices x and y does not exist in T1, but exists in T1 star. It is pretty much very clear that T1 and T1 star are complements of each other in terms of the edges. So, you can look at the picture, it is very clear to see and quite obvious that these 2 graphs are complements in terms of the edges, but the vertices remain the same, and you can see that this isolated vertex is also there, and therefore, T1 star is a cotree of T1. Similarly, T2 star is the cotree of T2, and here also we do not have the edge E1 here, we do not have the edge E5 here, E7 does not exist and E4 does not exist here. Likewise, the edges that do not exist in this graph exist in these graphs. So, T2 star is the cotree of T2. So, this is how we understand cotrees. Now, let us see some theorems that relate the connectedness property of a graph with that of a spanning tree. So, the theorem is that G is a connected graph if and only if graph G has a spanning tree. So, you can see that a graph is said to be connected if and only if. So, you can see that it is a necessary and sufficient condition for a graph to be connected is that it should contain a spanning tree. And now, let us see the proof of this theorem. Now, the assumption, let us assume that G be a connected graph. In that case, I have to prove that G has a spanning tree. So, the first part is that I assume that G is connected, and let T be a minimum spanning subgraph of G. We will be proving that T is the required spanning tree later on at the end of this part of the proof. So, for now let us assume that T is a minimum spanning subgraph of G. So, since it is a minimum spanning subgraph, T minus x is going to be disconnected by the removal of even one edge. That edge can be any edge in the edge set of R T, which is the minimum spanning subgraph. So, t minus x is disconnected by any x belonging to edge set of t, which implies that by this property I can call x to be the bridge of g of t. So, x is the bridge of t, which means that t is acyclic. So, why is this? Because if you can see this graph and let us say that t is a tree, and if the removal of one edge is causing the tree to collapse, then x is said to be the edge. So, only with the addition of that edge the graph becomes cyclic. Without that edge it becomes acyclic. So, clearly t has to be acyclic, and by our definition of tree, now we have a t which is a connected acyclic graph. So, we know a tree is connected and acyclic. Therefore, I can call t to be a tree, and we say that t is a minimal spanning subgraph of G and t is a tree, then obviously t is to be the minimal spanning tree. So, this is therefore G has a spanning tree inside it. So, from this we assume that G is connected, and now I have proved that G has got a spanning tree. Now, let us come to the second part of the theorem. Now, I have to assume that G has a spanning tree, and now I have to prove that G is connected. So, let us assume that G has a spanning tree. If it is a spanning tree, then obviously there is a UV path existing in the tree for every u comma v belonging to the vertex set of T. So, from this it is quite obvious that G is connected. So, from this part, so G has a spanning tree I assumed, and I have proved that G is connected. So, that proves the theorem of connectedness and G being a spanning tree. Let us now see a corollary to the theorem that we just studied. Suppose G is a connected graph with n vertices and m edges, then m is greater than or equal to n minus 1. So, m is the number of edges and n is the number of vertices. Then we say that the number of edges in the graph is greater than or equal to n minus 1. That is the corollary that we are going to study now. Now, you have a connected graph G, let G be a connected graph. Then by the theorem that we just studied, G has a spanning tree, say T. Then clearly T has n minus 1 edges since T is a tree. So, if it has n minus 1 edges, then the number of edges, which is m, is greater than or equal to n minus 1. So, that proves our corollary. Now, let us see the next theorem. Let T be a spanning tree of a connected graph G if x is equal to uv is an edge of G not in T, then T plus x contains a unique cycle. We shall be seeing the proof of this theorem now. So, I have simplified the statement like this. So, if T is a spanning tree of G and x is equal to uv be the edge belonging to the edge set of G, and this particular edge is not in the spanning tree that we constructed, then T plus x. So, by adding this edge to the original spanning tree, then you get a unique cycle. So, we will be proving that it first contains a cycle, then we will be proving the uniqueness. So, the proof is quite simple. Suppose T is the spanning tree of G, then for all cycle C belonging to T plus x contain x. Why is that? Because the tree is said to be acyclic. There is not going to be any cycles in the spanning tree T. So, if you can look at this picture here, so imagine the tree to be something like this. You have the vertices u, you have the vertices v, but there is no cycle. So, perhaps there is a path starting from some vertex and then going through u and then traveling somewhere and going to v, and then so this is actually a uv path, this small hump that I have drawn. So, uv, there is a uv path somehow. So, you can imagine we have simplified a graph here, and then you go on to other vertices. So, this is how a tree will look. So, it might come close to forming a cycle, but it will never form a cycle because a tree is basically a cyclic graph. And so, now imagine you are drawing this vertex u and you are connecting an edge from u to v by x. Immediately you are getting a cycle here. So, that is the meaning we are talking about here. Therefore, for this cycle C belonging to T plus x, every cycle, any cycle you think of here is definitely going to contain this edge x here. Since other than the x here, it immediately becomes acyclic. So, this is why we say that every cycle will in T plus x will contain this particular edge which connects u and v, namely x. So, what can I say about this? The observation that I make from this condition is that there exists a one-to-one correspondence between every cycle C belonging to t plus x and every uv path in T. So, that is quite obvious as I explained from these two pictures. So, which means that because there is a one-to-one correspondence, you can say that there exists a unique uv path, belonging to the tree T, which implies that there exists a unique cycle C belonging to t plus x. Therefore, that proves our theorem that t plus x contains a cycle and that t plus x, the cycle, is unique. Let us see a theorem now. G is connected and G has exactly one spanning tree T implies that G is equal to T. So, what we need to prove here is that if G is a connected graph and G is having exactly just one spanning tree. So, you know that in the examples that we saw before, it is possible to construct different spanning trees for any graph. But suppose you have a graph in which there is only one spanning tree, then obviously the graph G and the tree T are the same. That is the statement of this theorem. And how are we going to prove that? Is we are going to assume the following statement, that is, G is connected and G has exactly one spanning tree T, and now I have to prove that G is equal to T. Now, suppose not, we are going to go by proof by contradiction. So, suppose not, then in that case, even if there is one edge which is inside G but not inside T, then we can that is how we start the contradiction, and therefore, let x belong to the edge set of G and x does not belong to edge set of T. And suppose then in that case what happens is that you are able to find an edge which is inside G but not inside T. When this is the case, it is easy to create another spanning tree T dash, for example, and this particular T dash has the edge x. So, it is possible to construct another spanning tree with this edge x. In that case, what happens is that we arrive at a contradiction to the original statement that G is connected, that G has exactly one spanning tree. Now, I have constructed a new spanning tree and this is a contradiction to our assumption, and therefore, you can say that there is no such edge that exists in G but not in T, and therefore, due to this contradiction we can say that G is equal to T. Hence the theorem. Let us see the next theorem. An edge x of a connected graph is in every spanning tree of G if and only if x is a bridge. So, we have given a necessary and sufficient condition for a certain edge to be a bridge using spanning trees. Now, let us see the statement. So, this is a theorem. I have simplified the theorem statement like this. So, x belongs to edge set of G and x belongs to the edge set of T for all T where T is the spanning tree of G. So, this is the assumption, and you have to prove that this necessarily and sufficiently proves that x is the bridge of G. Now, for the first part, let us assume that x belongs to the edge set of G and x belongs to the edge set of T for all spanning trees T, for every spanning tree T, and you have to prove that x is a bridge. Suppose not, we are going to go by proof by contradiction. Suppose x is not a bridge. If it is not a bridge, then obviously the removal of that particular edge does not affect the connectivity of the graph, and therefore, G minus x is connected. If G minus x is connected, then by the theorem that we already studied, every connected graph is said to have a spanning tree. So, if G is connected if and only if it has a spanning tree, using that condition, since G minus x is connected, there is definitely going to be a spanning tree T belonging to G minus x, and let T be the spanning tree, and this x does not belong to the edge set of T. So, this means that this is a contradiction to this original statement that we have already assumed that x belongs to the edge set of G and x belongs to the edge set of T. Now, I have created a new graph G minus x, and this G minus x has a spanning tree which does not contain x. So, now let us see the converse part of this theorem. Let us assume that x is a bridge, and I have to prove that this edge x of this connected graph is in every spanning tree of G. So, that is the statement that I have to prove. So, assuming that x is a bridge, I need to prove, like I said, I need to prove that this x is in every spanning tree. And suppose not, let us go by proof by contradiction once again. Suppose not, then by negating this statement I arrive at this statement, that is, there exists a single spanning tree, there exists at least one spanning tree T such that X does not belong to the edge set of T. So, which means that then you get from this what I can arrive at is that T is a spanning tree, but this T does not contain X. So, what can I say is that T is the spanning tree of G minus X, but we already know that G is connected if and only if G has a spanning tree. I have now said that T is a spanning tree of G minus X. This implies that G minus X is connected. So, this means that by the removal of X from G does not affect the connectivity of G, which is a contradiction to the statement that X is a bridge. See, if X is a bridge, the removal of the bridge results in a disconnected graph. But here we are getting the contradiction that G minus X is still connected. For this is a contradiction to our original assumption that X is a bridge, and therefore from this I can say that X belongs to the edge set of T for all spanning tree T, thereby proving the statement. Theorem 5. A maximal acyclic subgraph of a graph G consists of a spanning tree from each component of G. The proof: let H be any component of G and let F be a maximal forest in G. We claim that F intersection H is a spanning tree of H. Assume that F contains all vertices of G. If not, let us add the missing vertices in G as isolated vertices to enlarge the forest. Since F contains no cycles, F intersection H contains no cycles. Also, F intersection H is a subgraph of F. Now, we have to prove that F intersection H is a connected subgraph of H. Suppose not, then F intersection H has at least two components. Clearly, H contains an edge between two of these components, since F is a spanning graph and H is a connected graph. Adding this edge to F and F intersection H, since F previously has no path between its end vertices, it cannot create a cycle. Thus, the resulting F obtained is a larger forest due to more edges. This is a contradiction to the original assumption that it is maximal. Hence, F intersection H is a connected subgraph of H. Thus, F intersection H is an acyclic connected subgraph of H. Hence, F intersection H is a spanning tree of H, and hence the theorem. Theorem 6. Every connected graph G with exactly two non-cut vertices is a path. The proof: let G be a connected graph with exactly two non-cut vertices. To prove that G is a path, we know that every connected graph has a spanning tree. Hence, G also has a spanning tree. Every end vertex of a spanning tree is not a cut vertex, since deleting an end vertex results in a tree on the remaining vertices. Hence, every spanning tree of G has exactly two end vertices and is a path. Consider a spanning path of G with the vertices V1, V2 and so on up to Vn in order. If G has an edge Vi, Vj with I less than j minus 1, then adding Vi, Vj to the path creates a cycle. Now, deleting Vj minus 1 Vj from the cycle results in another spanning tree with 3 end vertices. Hence, G has no edge of the path, that is, G is a path. Next, let us see the following theorem, Theorem 7. An edge of a connected graph is a cut edge if and only if it belongs to every spanning tree. Proof: let T be a spanning tree of a connected graph G. Suppose T omits an edge E. Then E belongs to the cycle in T plus E and hence is not a cut edge of G. Conversely, suppose that E is not a cut edge of G. Then G minus E is a connected graph, hence G minus E has a spanning tree T. Clearly, T is a spanning tree of G, hence some spanning tree of G omits E. Now, let us see the definition of a cut set. A cut set of a connected graph G is a set S of edges with the following properties. The removal of all the edges in S disconnects G. The removal of some but not all of the edges in S does not disconnect G. Let us see a simple theorem concerning spanning forests. If T is any spanning forest of a graph G, then each cut set of G has an edge common with T. Each cycle of G has an edge common with the complement of T. The proof: let T be any spanning forest of a graph G. Let C star be a cut set of G, the removal of which splits a component of G into two subgraphs H and K. Since T is a spanning forest, T must contain an edge joining a vertex of H to a vertex of K. Obviously, this edge is a required edge. Hence, each cut set of G has an edge in common with T. Let C be a cycle of G having no edge in common with the complement of T. Then C must be contained in T, which is the contradiction. Hence, every cycle of G has an edge in common with the complement of T. Next, let us see the following proposition. Proposition 1. Let T and T dash be spanning trees of a connected graph G. If E belongs to the edge set of T minus the edge set of T dash, then there is an edge E dash belonging to the edge set of T dash minus the edge set of T such that T minus E plus E dash is a spanning tree of G. The proof: let T and T dash be spanning trees of a connected graph G. To prove that T minus E plus E dash is a spanning tree of G, we know that every edge of a tree is a bridge. Since T is a spanning tree, every edge of T is a bridge. Clearly, T minus E is disconnected. Let S and S dash be the two components of T minus E. Since T dash is a spanning tree, T dash is connected. Hence, T dash has an edge E dash with its end in S and S dash. Thus, T minus E plus E dash is connected and has n of G minus 1 edges. Hence, T minus E plus E dash is a spanning tree of G. Let us see the next proposition. Proposition 2. Let T and T dash be spanning trees of a connected graph G. If E belongs to the edge set of T minus the edge set of T dash, then there is an edge E dash belonging to the edge set of T dash minus the edge set of T such that T dash plus E minus E dash is a spanning tree of G. Proof: let T and T dash be spanning trees of a connected graph G. To prove T dash plus E minus E dash is a spanning tree of G. We know that adding one edge to a tree forms exactly one cycle. Since T dash is a spanning tree, T dash plus E contains a unique cycle, say C. Since T is a spanning tree, T is a cyclic. Hence, there is an edge E dash belonging to the edge set of C minus the edge set of T. Now, deleting the edge E dash from T dash plus E breaks the only cycle in T dash plus E. Thus, T dash plus E minus E dash is connected and acyclic. Hence, T dash plus E minus E dash is a spanning tree of G. The next proposition, proposition 3. For 2 less than or equal to k less than or equal to n minus 1, the graph on n vertices obtained by adding one vertex adjacent to every vertex of p n minus 1 has a spanning tree with diameter k. The proof: consider the path p n minus 1 and let the order of its vertices be v1, v2 so on up to vn minus 1. Let G be the graph obtained by adding a vertex, say u, adjacent to all the vertices v1, v2 so on up to vn minus 1. Consider the graph T consisting of the path v1, v2 so on up to vk minus 1 and the edges uv1, uv2 so on up to uvn minus 1. Clearly, T is an acyclic graph. Also, the diameter of T is k. Thus, T is a spanning tree whose diameter is k. Hence, G has a spanning tree with diameter k. We have some more propositions too regarding the spanning tree in the script. You can refer to them. Now let's move on to the algorithm for finding a spanning tree. The procedure is: step 1, arbitrarily choose a vertex and designate it as the root. Then add all the edges incident to this vertex such that the addition of edges does not produce any cycle. Step 2, the new vertices added at this stage become the vertices at level 1 in the spanning tree. Arbitrarily order them. Step 3, next, for every vertex at level 1 visited in order, add each edge incident to this vertex to the tree as long as it does not produce any cycle. Step 4, arbitrarily order the children of each vertex at level 1. This produces the vertices at level 2 in the tree. Step 5, continue the same procedure until all the vertices in the tree have been added. Step 6, the procedure ends since there are only a finite number of edges in the graph. Step 7, a spanning tree is produced since we have produced a tree without cycle containing every vertex of the graph. Conclusion: in this module we saw some definitions of spanning trees, of cotrees, and we also saw some of the properties of spanning trees. We also saw how the property of spanning trees affects other properties of the graph, and we also saw some of the propositions related to spanning trees. We even saw an algorithm to construct a spanning tree. I hope that this module was useful. Please try to do the problems in the assignment and in the quiz, because we learn by doing. Thank you.